All right, so here we are with lesson 3, and this sort of culminates some of our law of sines, law of cosine stuff when we get into the applications. But first, we got to clear up some things here about vectors. All right, and you'll see some things come back to us here that we had in earlier units. I'm going to give you a minute. You can push pause here and just read through this. I already filled in the blanks for you. You can fill in your blanks. And then sort of each of these pieces is what we're going to work through in our notes. So go ahead and push pause and then read through that real quick. All right, so geometric representations of vectors. Okay, so a vector in standard position means that the initial point of the vector is at 0, 0, and the terminal point is at whatever coordinate or point, okay, that is designated. So again, initial point, all right, you'll also hear that called the tail, all right, and terminal point, you'll hear that called the head of the vector. All right, so if I were to draw vector AB here, okay, I would put my initial point at 0, 0. All right, and let's say that vector AB equaled 4, 3. All right, I would go over 4 and up 3 to put the head of my vector. I would draw a straight line segment and put an arrow at the end of the line. That's what designates it to be a vector. All right, so again, the 4 is like an x value, the 3 is like a y value. All right, we'll also refer to those as I and j when we write in vector notation. Okay, and this ends up, being a right triangle if I draw the components of my vector in. So my x component will be 4, my y component will be 3. So you'll see how Pythagorean theorem and other things are going to come into play when we talk about vectors. All right, so there's a couple different ways we can write a vector. Okay, we can write it in, first we could write it in component form. If we write it in component form, we would simply say 4, 3. All right, it would be similar to a coordinate, but notice these symbols are a little different. Okay, if we were going to write it as a linear combination, again, these are words that were in the blurb above. So as a linear combo, we would say 4i plus 3j. All right, so again, we call that a linear combination because it sort of looks like a linear equation. All right, so those are two ways that you can describe a vector. We're going to see some more. All right, so magnitude or the norm of the vector is the length, so to speak, of the line segment. Sometimes, though, it's a velocity, so we call it a length, but it might be labeled as different. Okay, so let's take a look here. All right, let's just say we were talking about that same vector from last time. Again, it wouldn't matter if it was vector 4, 3 or whatever. Okay, so let's say it's vector 4, 3. All right, and I wanted to find the magnitude of the vector. Well, we just drew in what that right triangle would look like when we break it into component form. All right, which tells us we're going to be using Pythagorean theorem to find the magnitude of the vector. And you can read through the blurb up here. This is no more than your distance formula. Okay, this is Pythagorean theorem. So there's a variety of ways that you can find the length of the vector. Okay, Pythagorean theorem is probably the easiest. So this would be a 3, 4, 5 triangle. So the magnitude of vector v would be 5. Okay, and again, the symbols we use for magnitude look like that double absolute value bar. All right, so let's take a look at another example here. So sketch and find the magnitude of vector v. All right, here the vector is given to us as negative 2i plus 3j, so that's linear combination form. So that basically tells us an x and that tells us a y component. So if I come over here and draw my vector, negative 2 and 3, all right, that would be the head of my vector, tails at the origin, unless otherwise stated. Okay, and if I want to find the magnitude of that vector, I'm going to have to break it into its components, all right, which would be the x and y value, 2 and 3, and then use Pythagorean theorem to find it. So 2 squared plus 3 squared equals c squared. So it looks like that's going to be 13 equals c squared. And if I square root both sides, I'm going to leave that in radical form. My magnitude here would be root 13. Okay, so I would say that the magnitude of vector v equals the square root of 13. All right, what about an example where it's not in standard position? Okay, so this vector here has an initial point at 4, 1, a terminal point at 7, 5. Excuse me. So if I draw my initial point 4, comma 1, and I go to 7, 5 from my terminal point, okay, all the same processes occur, okay? All I'm still doing is turning this into a triangle, determining what the components of the vector are. So this would be 3. All right, that would be 4. Then I'd be doing Pythagorean theorem to find the magnitude of the vector. Again, that's a Pythagorean triple, so it ends up being 5, as the example above. But all we're trying to show here is that this vector may or may not be in standard position. All right, so find the component form of the vector. We would say that's 4, 3. And find as a linear combination, that would be 4i plus 3j. Okay. Excuse me. All right, so what about vector addition? All right, so tail to tip rule. So basically we're going to slide one vector so that the tail of it is connected to the tip of the other vector. Okay, so what we'll have here, if we're doing something like vector u, all right, let's call vector u 4, 1. Let's call vector v 1, 3. Okay, so if we're adding those two vectors together, the nice thing is you can actually add them in component form. So it's literally like, combining like terms, if you will. So 4 and 1 make 5. So we'll call the new vector w. Well, let's call it u plus v, so it's not confusing. So u plus v would end up being 5, comma 4, right? So that tells us, what that new vector is going to look like, okay, or the resultant vector, okay? But if we were actually going to add that together, what we would do here is, let's see, I would have 4, 1, so there's that vector, okay? And then I would go from, and then I would have 1, 3, all right? So that's this vector. But what I would want to do is take that vector and I want to expand it. Take that vector and slide it to the end of that one, right? And that's how we do tail to tip addition, because what happens is your original initial value and then your new terminal value or point, okay, are going to create that resultant vector. Glitching on me here. Okay, and look where that happens to be, over 5 up 4. Okay, and we'll talk about how we can also add these together when we're not on the coordinate plane, all right, in a future example. Subtraction works the same way, okay? It's just your second vector you got to make negative, okay? So if you would be doing u minus v, then v would be the one that's -1, -3, okay? So if we were in component form again, we did u minus v, that would have to be 4 minus 1 is 3, right? And then 1 minus 3 is -2. So that kind of tells me where it's going to end up. But if I was doing the tail to head addition, I would have to flip one of my vectors. It would be pointing the opposite direction of what it is to be able to show that graphically. All right, other vector operations. Again, this stuff's pretty easy here. It's a lot of combining like terms, adding, subtracting, basic multiplying. We're just applying it to a different scenario here. So 2v plus w. So again, I'm going to do 2, and then I'm going to write vector v in here. Okay, and then I'm going to add vector w to it. So 2 times -3 is -6. All right, 2 times 5 is 10. And then I add that to vector w. All right, so -6 and 2 is -4. 10 and 4 is 14. So my resultant vector would be -4, comma 14. So again, if I were to do this graphically, it'd be very simple. I would draw vector v, -3, 5. I'd double its length, so it'd actually be -6, 10. Think about that for a second. And then I would drag vector w to the tip of it, okay, and match it up, and then that would put me at -4, 14. All right, so let's see here. What do we got? W minus v. Okay, so if I have vector w, which is 2, 4, and then I have vector v, which is -3, 5, I'm just going to subtract the similar terms. So the x terms go with the x terms. 2 minus negative 3 is 5. 4 minus 5 is negative 1. So my resultant vector would be 5 and negative 1. All right, a unit vector, okay, so vector has the same direction, all right, as a non-zero vector, but it has a length of 1. Okay, so the magnitude, it's kind of like the unit circle, is 1 always. Okay, so the way we do that is we find the magnitude of the vector and then we divide the components by the magnitude, if that makes sense. All right, so we're basically like downsizing it, if you will. All right, so find a unit vector in the same direction as vector v, which is 3i minus 4j. So the first step will be to find the magnitude of vector v, which is pretty simple, right? We can see right here the horizontal component is 3, the vertical component is 4. So regardless of what direction this vector goes, it does make a 3, 4, 5 triangle, okay? If it wasn't a 3, 4, 5, you just have to use Pythagorean theorem to find that side, okay? So the magnitude of vector v is 5. If I want to find the unit vector, I simply take the vector I have and I divide its components by the magnitude. So vector v, new vector v here, unit vector v, is going to be 3/5 I plus, or excuse me, minus, keep it the same direction, minus 4/5 j. Okay, and it's kind of funny how that works out, but if you were just to do the Pythagorean theorem then on 3/5, okay, squared plus 4/5 squared, right, you would get 9/25 plus 16/25, which equals 25/25, all right, 25/25, which is 1, okay, which satisfies this being a unit vector, length of 1. All right, but again, here was the answer. I was just proving it down here. All right, equal vectors, only ones that are equal here are same direction, same magnitude. Okay, so if they're same direction, same magnitude, all right, they would be equal vectors. Same magnitude, all right, but some different direction, whether it's opposite or otherwise, then they're not equal. Same magnitude only, okay, but completely different directions. And then you have just different magnitudes, okay? Those would not be equal vectors. Direction angle of a vector, again, a lot of right triangle trig here. So the direction angle of a vector is the positive angle from the x-axis to the position of the vector. We're going to use a lot of tangent for this. All right, you see here, use some tangent. If we know the length of the vector, all right, then we can use sine and cosine to find its components, all right, when those things aren't given. All right, so, and again, that still all stems from what we did with the, back in the earlier parts of the semester, okay? Knowing that the x component, all right, versus the y component, all right, and if this is theta, okay, the way we relate to three of them is using tangent, all right? So tangent of theta is y over x, you already know that, okay? And if you know the magnitude of the vector, let's call that vector v, right? That's where cosine tells you the x component. So v times the cosine of theta gives you the x component, all right? And then v times the sine of theta gives you the y component. That's all review stuff, all right? Just taking it from the unit circle now, applying it somewhere else. So find the direction angle of vector v if the vector is described as negative 2, 5. Okay, so that vector is going to start at the origin, all right? It's going to go negative 2, 5, all right? So that will be the terminal point of the vector. I'm going to connect my dots there, and then if I want to find the direction angle, it's from the positive x-axis, so it's this angle here. Okay, so I'm going to have to probably find this one first and just subtract that from 180. I'm going to go ahead and draw in my right triangle. I know that this is a 2, I know that that's a 5. I'm going to do tangent of theta equals 5 over 2. So that means that theta is going to be the inverse tangent of 5 over 2. All right, I'm going to jump out here. Inverse tangent of 5/2 is 68 degrees. So theta being 68 degrees is not my answer, right? I need to take 180 minus that 68 degrees, all right, to get 112 degrees as my direction, okay? So the direction would be 112 because it always goes from the positive x-axis, regardless of what quadrant you're in. All right, find a vector whose magnitude is 6 and the direction is negative 3, 3. All right, so they're not telling us where the actual terminal point of the vector, they're just saying it's going in that direction. All right, so to do that, we would have to use the tangent value here. All right, so tangent of theta, all right, is going to equal my y component, which is 3 over my x component, which is negative 3. So if I do inverse tangent again, all right, that's going to give me the angle of my vector, which in this case ends up being 135. Okay, so that puts me in the second quadrant. All right, 135. All right, remember that's the angle from the positive x-axis. All right, now if the magnitude of my vector is 6, I can find the components of my vector. All right, don't be fooled here. They weren't 3 and negative 3. It's just telling us that's the direction of it. Okay, so what we would want to do is use the magnitude of the vector. All right, make a generic triangle here. We don't know what the lengths are yet, but we can find x using cosine and we can find y using sine. And the length of our vector is 6. Right, so if I'm setting up, if I'm setting all this up, okay, then I would have, let's see here, 6 times the cosine of 135, that's my direction, and that's going to give me my I component, or my x component, all right, and then I'm going to have 6 times the sine of 135, and that's going to give me my j component, or my y component. This is all right triangle trig stuff here that we've already done before. All right, so if you need a step before that, all right, it would be the cosine of 135. All right, the step before would be cosine of 135 equals x over 6, right? Adjacent over hypotenuse. It all goes back to geometry, all right? So when I plug those in, again, I could use the unit circle to get these, or I could actually calculate them. Since 135 is a unit circle, I'm going to go ahead and just use that. So that's going to be 6 times negative root 2 over 2. And then this is going to be 6 times positive root 2 over 2. So I end up getting negative 3 root 2, and I end up getting 3 root 2. All right. Now, if I wanted that as a linear combination, I would go negative 3 root 2i plus 3 root 2j. All right. If I wanted it just as in vector notation or component form, then I would do negative 3 root 2 and 3 root 2. All right. Okay, so find the measure of the angles between forces 80 pounds and 70 pounds if the magnitude of the resultant force is 98 pounds. Okay, so what we're looking here for is the angle between them. So in other words, we have one force, okay, of 80. All right, doesn't really matter what direction that goes in. All right, then we have another force of 70. All right, so that's 80. And that's 70. It tells us the resultant force between those two is 98. So what you'll notice here is that we basically end up with a side situation with the law of cosines, which is why we just got done covering that. So if we're looking for the angle between the forces, okay, then that would be, believe it or not, that would actually be this angle here. Okay, because remember that originally there was a force, there's a force, so this is the angle between them. But remember, when I'm adding vectors, like I told you earlier, I'm going to slide that vector down. Okay, so we'll talk about how we find that. First, we're going to just find some angles in the triangle. Okay, would help. All right, so let's see here. The angle that I really need is this angle here. So when I set up my law of cosines, okay, I'm going to do, let's see here, cosine of theta equals, let's see, 80 squared plus 70 squared minus 98 squared. We just got done doing this. divided by 2 times 80 times 70. All right, I'm going to end up doing the inverse cosine of all that. But remember, when I told you to do this, we're going to type the whole numerator in first. So 80 plus 70 minus 98. So 80 squared plus 70 squared minus 98 squared gives me 1696. All right, so 1696 over 2 times 80 times 70. 2 times 80 times 70 gives me 11,200. 11,200. All right, then we do the inverse cosine of that. So second inverse cosine of 1696 over 11,200 gives me 81 degrees. All right, so theta equals 81 degrees, but again, that's not the angle between the vectors, right? If I slid that vector back down here, all right, where it would have started, that 70-degree vector, okay, would have, whoops, glitching on me again. That 70-pound vector would have been down here somewhere, okay? I'm actually looking for that angle right here, all right, which would be equivalent to this one right here. All right, so that's 180 minus 81, all right, is how I would find that. So that's 99 degrees, right? Okay. All right, so find the magnitude and direction of the sum vector W if two vectors U and V of magnitude 6.9 and 13 respectively, if the angle between them measures 48 degrees. So again, so here is one vector of 6.9 length. All right, here is another vector, okay, of 13 magnitude, and it's telling us the angle between them is 48. You can't add vectors using tail to tail, it doesn't work. All right, you have to use tail to head. So again, I slide the vector. All right, I'm going to slide that 13 magnitude vector down to here. Okay, the resultant vector from the original tail to the new terminal point is my the one I'm looking for. Okay, now keep in mind in doing that, notice how the angle slid with it. I don't know any angles now. Okay, so if I kind of draw a new picture here, because that one looks a little sloppy, I'm going to have 6.9 here for this vector. All right, this vector here is 13. Okay, the resultant vector connects the two together. And I know that this angle here is going to be 180 minus 48, okay, which is what, 132? Okay, so if I'm looking for the magnitude of the resultant vector first and then its angle second, I'm going to have to find the magnitude here of this vector, okay, and we're calling that vector W. All right, so that is another law of cosines problem. So W squared equals 6.9 squared plus 13 squared minus 2 times 6.9 times 13 times the cosine of 132. And you can type all that in at one time, okay, and square root your answer, and you should get 18.3 units, but let's do it just to make sure. Okay, so we have 6.9 squared plus 13 squared minus 2 times 6.9 times 13 times the cosine of 32. All right, and then if I square root my answer, I get 18.3. Okay, so that's the length of that vector. All right, now if I want to find the magnitude of the vector or the direction angle, I'm going to have to solve for this triangle in my diagram. Okay, or that angle in my diagram. So I can use anything now. I have side, 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 so I can use law of cosines. I can use law of sines. So sine of 132 over the side I just found, 18.3, equals the sine of theta over 13. Cross multiply and solve, and I'm going to get 16 degrees for my side. Oops, that looks like 76. 16 degrees, all right, from my direction angle, okay? And the rest of these sort of set up the same. I'm not going to, these last two here, if we get to those in class, we'll go over those in class if you don't do them today. Otherwise, good luck and have a good day.